Thanks a lot, Thomas, for the introduction. So please interrupt me at any point when you have questions. I hope it's fine by the chairman. So I'd like to begin by thanking the organizers, Thomas, Jairo, and the others for putting together this exciting workshop, and especially for giving me the opportunity to share these nice results with you all. I should also thank the SPICE team, especially Jairo, for keeping the center running and continuing to host these inspiring workshops in Mainz. So I flash on the screen 3 statements about antiferromagnets which are encountered in different contexts. In this talk, using concepts from the field of quantum optics, we will look closely at the quantum nature of antiferromagnetic magnons, thereby connecting all these 3 different statements. In particular, we'll be interested in exploiting antiferromagnetic magnons for causing interactions between fermions, leading to condensation phenomena, superconductivity being a prime example of that. To this end, let's begin with the motivation. So if we have electrons in a background, the electron can deform the background, which is a lattice in this case, and this deformation tends to attract another electron towards it, which could give rise to electrons pairing up into Cooper pairs, giving rise to superconductivity. At a more quantum level, this process is seen as one electron, which emits a phonon to be absorbed by another electron at a later time. This gives us to an attractive interaction. If we do the simplest BCS theory for this, we find that there's a critical temperature corresponding to the superconductivity, which can, in a simple way, be expressed in this format. Here, this omega c is the energy scale of the phonons which are being exchanged. This will be typically the Debye energy, a few hundred kelvins. And this lambda captures the interaction strength between the electrons and phonons and some other parameters. So typically what happens in conventional superconductors like aluminum is that we have a very large couple of hundreds of kelvins energy scale, which is exponentially suppressed because of the weakness of the electron-phonon interaction by this lambda parameter. And the net result is you get a TC, which is really small. Now for our community, in the recent years, it's been discussed that if we have these magnet-metal bilayers, one can envisage the same kind of interaction, but now mediated by the magnons which exist in the adjacent magnetic material. Under such a condition, this energy scale will simply become the magnon energy, and this lambda will parameterize the electron-magnon coupling strength that comes from the interfacial exchange interaction. This was a theoretical motivation, but a long time ago in 1990, Mudera and Meservi at MIT found that when they deposited bismuth and gallium on nickel, the critical temperatures increased. So bismuth itself, in its elemental form, is not superconducting at all, but when deposited on nickel, it exhibited a critical temperature of 3.7 Kelvin. And for gallium, it's superconducting with 1 Kelvin critical temperature, but when deposited on nickel, it increased to something above 4. At that point, this was not well understood. There were some speculations this could be structural effects, but then I spoke to Dr. Mudera, and he said that those speculations were not adequate at that point. So this was at that. More recently, nickel-bismuth system has been studied once again, but this time not with transport measurements, but more with optical measurements. So this shows curve rotation measurements using such a setup. The main message here is that they found that the curve rotation indicates that the superconducting order parameter has a net spin. It has a magnetic moment. And this was, in combination with some theoretical arguments, has been used to say that this can only be if the superconductivity is magnon-mediated. This is probably not a smoking gun, but this is suggestive, and this is the current understanding as per this article here. So having said the motivation, this is the plan for the talk today. We'll be looking at the spin excitations in ordered magnets very carefully. The term magnon has been used in literature in a very general sense to label excitations which are very different from each other at the quantum level. As a result, in this talk, I'll have to use some funny names, borrowing terminology from the field of quantum optics, but I want to emphasize beforehand that I'm simply talking about the excitations which you are all familiar with as magnons. Okay, so let's start with looking at a ferromagnet. A perfectly ordered ferromagnet can be depicted in a simple way with such ordered state. For I want to create the lowest excitation, what I do is I flip one spin, but it's more convenient to look at this state as an ordered ground state on which a spin flip, the so-called localized magnon, has been superimposed. When one considers only exchange interaction and Zeeman energy, such an excitation gets delocalized over the whole space and becomes the eigenexcitation of the system. This exact entity is what I will be referring to as magnons, and we'll encounter some different entities in the future. All right, so let's get the terminology straight. So this, I will depict the fully ordered state or the ground state with such notation, and one magnon like that, and two magnon, and so on. Now let's look at the ground state once again. For simplicity, let me just look at the sum of the total spin in the ground state. In other words, now I'm looking at the k equal to 0, the uniform mode. Okay? So I can depict this, since this points along the z direction, I can depict this in the so-called phase space, the sx and sy plane, as such a dot in the origin. However, this is not strictly allowed by quantum mechanics because spin Sx and Sy are two non-commuting quantum observables. As a result, they have to be, this cannot be determined at the same time. So the picture allowed by quantum mechanics is more like this, where this shaded region represents the Heisenberg uncertainty region. Okay, so we have a Heisenberg uncertainty. Nevertheless, the ground state still remains what we started with, the fully ordered state. Now let's imagine what happens if, for some reason, we have anisotropy in the system such that it costs a higher energy to have spin in the y direction. So if I introduce such a Hamiltonian, to minimize energy, the system switches to its Heisenberg uncertainty region to have such a shape. Now in the original basis, this is represented by a coherent superposition of the different even magnon number states. For simplicity, I'm not showing the amplitudes of each of the states here, but we'll come to that later. And conveniently, this can be expressed as something called a single mode squeeze operator applied on the original vacuum. So I'm not going to show what the squeeze operator looks like, just a mathematical expression, but what we can appreciate is that this R is a so-called squeeze parameter. When R is 0, then this operator is just 1, and you have basically identity on both sides, and R parameterizes the extent of this squeezing. In this particular case, it's directly related to this ellipticity. And this concept comes from the field of quantum optics, where people asked a long time ago whether one can generate a state where the uncertainty in one physical observable can be decreased at the expense of an increase in the other. For the optics, the two observables are the electric field and the magnetic fields associated with the optical mode. And such ideas similar to this are being employed in the gravitational wave observatory to detect, to achieve detection sensitivities which go beyond the quantum ground state limit. What's very important to remember is that in the case of optics, this is a non-equilibrium state. This is not an eigenstate of the system. This is achieved via driving the system via amplifiers. In the magnetic system, we are talking about eigenstates of the magnetic system. Okay, so let's summarize how it goes. So we started with, when we had a Hamiltonian, isotropic Hamiltonian, the ground state was depicted like that. When we had this anisotropic Hamiltonian, the ground state became something like this. Now, if I wanted to create an excitation on my usual ordered state, then I simply add one magnon to my ground state. And if I want to do the same on this anisotropic system, I have to add a magnon to each of the constituent states, giving rise to this, the squeezed magnon excitation. And conveniently, they are still related by the same squeeze operator. And that's why, so this is basically what we already know as an elliptically polarized spin wave. This is simply a quantum depiction of the same concept that we are familiar from the LLG phenomenologies. So to summarize, the ferromagnetic part, the squeezing is caused, in this case, by anisotropies, and as a result is somewhat weak. What I mean by weak is that if I were to ask the question, how many magnons make up one squeezed magnon, the answer will come out to be something like 1.7, 2.1, depending upon the parameters. So although it's an appreciable number, it's still of the order of 1. And although in some experiments, or depending on what quantity you're interested in, it will be very important to take into account the superposition. But to my knowledge, all the experiments carried up to date are essentially unchanged, whether you consider this or that. We are missing something which is a factor of 1 probably. But what I want to emphasize now is that for antiferromagnets, this situation is completely different, because not anisotropy, but exchange causes such effects. Okay, so for antiferromagnets, for ferromagnets, we started with we had such a situation, right? For antiferromagnet, we have an anti-parallel second sublattice, which hosts another excitation of the opposite. Now, when these two sublattices are completely decoupled, this is the excitation landscape. But all the fun happens when we bring them together, then these excitations undergo major transformations that we will look at it now. Once again, I want to start by looking at the total spin on each sublattice. So I can look at these two vectors. Once again, I can draw the phase space, but I need two plots for this now. And Heisenberg uncertainty can still not be violated, so I have these uncertainty regions. Now, this is where the main distinction arises. So the dominant energy for an antiferromagnet is this antiferromagnetic exchange. The reason why we started by assuming such an antiparallel state is that it costs a lot of energy for the antiferromagnet to have spins not anticollinear. Okay. Now imagine this. Now, because of, if there was no Heisenberg uncertainty, this will stay like that, and this is the lowest energy ground state. Now, because of uncertainty region, these are forced to fluctuate. Okay. Now, if they are fluctuating independently, the angle between them is not 180 degrees. So what happens is, to minimize energy, instead of fluctuating randomly, they coordinate and they fluctuate like this. So they maintain their 180-degree angle, but the fluctuations become amplified. And this is exactly what happens. And so in the actual antiferromagnetic ground state, the two sublattices become quantum correlated. And in the magnon picture, this is depicted as giving rise to a large number of magnons on each sublattice. So once again, now we have, this was the Néel ordered state. This is the true ground state, which is, as we will see, it can still be approximated by a Néel ordered state. If I wanted to create an excitation, a spin-up excitation on my Néel ground state, I simply add this spin here, and then I have a simple magnon on one sublattice. But if I want to create a spin-up excitation on top of the actual ground state, what I have to do is have to add a spin-up on each of these states. And this is the true depiction of an antiferromagnetic spin-up magnon. And conveniently, this is again, we can use the same squeezing terminology, because now this is related to the original states by something called a two-mode squeeze operator. The interpretation in terms of ellipticity is a bit more mathematical here, so I will not go into that. But mathematically, these operators look exactly the same. And R still remains the squeezing parameter, and we'll come to the physical significance of this in a short while. Before the physical significance, let's look a little bit more at the maths. So if I now want to finally look at what are the different contributions of each of the constituent states, I can write this ground state as a sum over these constituent states, where Pn now becomes the amplitude of each of these states. In a similar way, Qn becomes the amplitude of each of the constituent states. Let's look first if R is equal to 1. I'm still being a bit abstract, but we'll come to what the physical significance of R is in a short while. So let's say when R is equal to 1, this blue curve depicts the ground state, and the red curve depicts the spin-up antiferromagnetic magnon. So what we see is that the contribution of subsequent larger n state is decreasing, and for R equal to 1, it dies out around when n becomes approximately 10. But when R is equal to 3, which is the case relevant for realistic antiferromagnets, then what we find is, once again, the contribution for the ground state is decreasing, except that now it goes on until something like n equal to 500. But most importantly, the contribution for the spin-up antiferromagnetic magnon, increases at first and then decreases. So the maximum actually occurs at n, which is not 0, but something of the order of 100 in this case. So the main message of this is that while it is reasonable to assume that the ground state has a maximum contribution from n equal to 0, that is the Néel ordered state, it is not reasonable to assume that the spin up antiferromagnetic magnon is dominated by here. So it actually comes from here, so it's best depicted by one of the states here in the middle. To get a feel for numbers, I can ask the question, how many up magnons make up this squeeze state? Then I get some answer which is like this. And the same question asked for the antiferromagnetic spin-up magnon gives me this answer. So this R, in that sense, parameterizes how large is this summation of the states. All right, so what does really R consist of? So if I consider now a uniaxial antiferromagnet, then I have the antiferromagnetic exchange term, and then I'll have the anisotropy terms. For this Hamiltonian, if I calculate now the squeezing parameter for the uniform mode, it comes out to be square root of j by k. And plugging in numbers for some typical parameters, I indeed find that R approximately 3 is the parameter that I get. To compare it with light, so with non-equilibrium generated squeezed light, the best case scenario so far has been an R approximately 1.7. So compared to that, the extent of squeezing in our antiferromagnets is very large, because physical observables vary exponentially with R. So the difference between R equal to 1.7 and R equal to 3 is an order of magnitude difference between the physical observables. Okay, so with this, let me sum up the antiferromagnetic magnon part. So as I mentioned before, the unique aspect for antiferromagnets is that exchange itself, which is responsible for causing order, it is also responsible for causing this squeezing, and as a result, it's also responsible for causing disorder. And these two effects compete. So this is why for antiferromagnets, it's extremely important, and these effects are large. So a way to depict, for simplicity, it's very hard to always show the superposition. So I'd say a schematic way to depict the antiferromagnetic ground state might be this way, and an antiferromagnetic magnon, I'll continue to depict it using such a simplified representation where number of upspins is one more than the number of downspins. Okay, so this is, in some senses, an old story. You already know about this excitation, so there is, mathematically speaking, this is not any new excitation. So what do we gain from looking at all these details of the wave functions and so on? So to understand that, let's look at how this antiferromagnetic magnon actually looks like. So this is the whole excitation, spin h bar. Now typically what we do is we think of coupling to the antiferromagnetic magnon as a whole. And then when something external couples to the antiferromagnetic magnon as a whole, it only sees the net spin of the excitation, which means the coupling is proportional to the net spin, which remains h bar. Now if we were able to engineer systems where we can couple only to one of the sublattices, then the external excitation bath sees a very large spin on one sublattice. As a result, the coupling is proportional to this very large spin and is very strong. And such a situation is, for example, obtained when you have an antiferromagnet coupled to a normal conductor and exposed via an uncompensated interface. So this corresponds to such a situation. This is just an example, but in general, any interaction which will be mediated by the sublattice spin and not the net spin will be greatly amplified for this. So a couple of years ago, we calculated the spin pumping current from a general two-sublattice magnet into a normal conductor, paying attention to the different possible interfaces. So this is the uncompensated interface, and this is the compensated interface. And what we found back then, to our surprise, is that the spin current is strongly enhanced as one goes from a ferromagnet to an antiferromagnet, and more importantly, as one goes from a compensated interface to an uncompensated interface. So at that point, it was not clear to us what the mathematics spit this plot out, but it was not clear to us what is really going on. But this picture now allows us to understand that it's actually the coupling between the magnons and the electrons, which increases because of these effects, which gives rise to a strong spin pumping current. This still remains a theoretical calculation. To the best of my knowledge, there is no experimental corroboration of this effect so far. So, should we really care about this? But luckily, there's experimental corroboration of the related effect. So this is quite an interesting paper on its own, but I will not have the time to go into the details of it. But I can simply say that an upspin magnon and the downspin magnon can couple via some mechanism, and when they couple, they can hybridize into a zero spin or a linearized magnon. And it so turns out that under such conditions, this coupling is indeed mediated by the sublattice spin and not the net spin. As a result, this coupling is amplified by the same factor that I showed you by approximately a factor of 100. And this has indeed been observed in experiments carried out close to room temperature, and this came out last month, I think. So now to compare it to the field of quantum optics, I want to bring your attention to these two papers, which were submitted on consecutive days and then appeared on the exact same day. These two papers also report essentially identical physics. And interestingly, the physics reported here is also mathematically analogous to what I'm talking about, the amplification effect that I'm talking about. Okay. So to compare these two ideas, so on this side we have the theoretical, these two papers were theoretical proposals. These are the actual experimental realization of this enhancement effect. This has to, like I said, in light, the squeezing effects is non-equilibrium. You need to drive to achieve this. On the other hand, on this side, we have it's an intrinsic property of the antiferromagnetic magnon. And finally, considering the best case squeezing that has been achieved with light, the expected enhancement can be as high as 10 for the case of light. On the other hand, the observed enhancement is closer to 100 in this case. The main message of this slide is that once we recognize this squeezing terminology for the magnons, then we can carry forward a lot of ideas directly from the field of quantum optics and apply them in our magnetic systems. And the second thing is that magnetic systems offer an intrinsic niche over the quantum optics field for implementing certain ideas, as kind of evidenced by this very high enhancement factors. All right, so finally, so let me come to the superconductivity aspect. So I started by introducing this slide and this expression. And I said that usually what kills superconductivity is that this lambda parameter, which parameterizes electron-magnon coupling strength, is small. So if you were to increase the critical temperature, if you would like to increase the critical temperature of a system, you should try to focus on this lambda. But this is exactly what we have just been talking about. So if I couple the system to the whole antiferromagnetic magnon, the coupling is weak. If I couple to only one sublattice, the coupling becomes greatly amplified, and as experiments show, it can be as large as 100. And if I use this idea, I would expect an enhancement in this lambda and hence TC. So with this motivation, we indeed carried out detailed calculations on such a system, where this is the toy model we use, where the coupling is allowed to be asymmetric, and this capital omega parameterizes the asymmetry. So when capital omega is 1, which corresponds to a compensated interface, and when capital omega is 0, it corresponds to a perfectly uncompensated interface. And after doing whole calculations and the details I skip, we obtain these plots where, using parameters available from experimental literature, we find that as you go from a compensated interface to an uncompensated interface, the TC shoots up from being something like a microkelvin to all the way to several tens of kelvins. So, and this is a direct consequence of an enhancement in the electron-magnon coupling parameter, as we just discussed. Of course, there are caveats here. This is a p-wave superconducting state, which is very sensitive to disorder, which we have not accounted for in these calculations. So it's a best-case scenario in some sense, or the ideal world scenario, but many details can make life difficult for experimentalists. All right, so let's now go to the final topic. Let's look very closely once again at what causes this electron-electron attraction for superconductivity. Okay, I'm taking an oversimplified picture here, but that turns out okay for the case at hand. So when I have electrons, right, they emit a phonon, which means the lattice has been deformed, and this deformation creates a positive potential, energy minimization for the other electron, which pulls it towards itself. Okay? The origin of attraction is purely Coulombic. It's charge-based interactions. And the moment I come to the magnon-mediated superconductor or magnon-mediated interactions, what happens is my electron emitted one magnon here, and this magnon decreased the net spin at that point, and that created an energy decrease for the other electron in the spin channel. So it's like a Zeeman energy. Effectively, the Zeeman kind of energy is what is causing this attractive channel in this case. Okay. But this is the case for a ferromagnet. But now if we have an antiferromagnet, as we just discussed, let's say my electron emitted an antiferromagnetic magnon here, which means it emitted this massive entity. Nevertheless, what happens now is electron emitted this massive entity, which reduced the spin on the blue sublattice by a large amount. As a result, this created a large attractive potential for the other electron. So this also enhancement once again makes sense from the physical picture. But what's interesting is what happens if I can do a coupling in this format. So my electron came from this side. It emitted this massive antiferromagnetic magnon. But on the other side, my electrons are only sensitive to the red sublattice. Then instead of seeing an attraction, the electrons are repelled by it because they see the opposite spin to that they were expecting. Okay? And this causes an electron-electron repulsion instead of attraction. And such an electron-electric repulsion can be seen as an electron-hole attraction. But before I go further with the electron-hole interaction part, I want to emphasize that this strange phenomena of repulsion will not work with phonons because there is no anti-correlated sublattices, and it will also not work with ferromagnetic magnons. This is fundamentally a property of antiferromagnetic magnon because of quantum coherent coupling between the two sublattices within one excitation. Okay. So since electron-electron repulsion, repulsion is not fun anyway. So when life throws lemons at you, you just make lemonade. So you have, instead of looking at electron-electric repulsion, we look at this as electron-hole attraction, which means if I were to use this across in a semiconductor with an N-type doped semiconductor and a P-type doped semiconductor, then I have electrons on one side and the holes on the other side, and this interaction causes them to attract each other, leading to indirect Exciton condensation. So for this Exciton condensation, the critical temperature physics is essentially similar to the superconductivity. We use the BCS series essentially, but the order parameters vary. So it's instead of forming a Cooper pair with two identical electrons, now this is pairing between an electron in this layer and a hole in that layer. So the order parameter is fundamentally different. And what's shown in this plot, which I probably shouldn't go more into the details, is the TC can be optimized by choosing the anisotropy and exchange ratios carefully. So it gives some sort of design equations that one can use to determine what's the best material and so on. So with this, I come to the end of my talk, not before thanking all the great collaborators who have contributed to the works that are presented here. So the theory work has mostly been carried on Trondheim, Constance, and Utrecht, and the experiments were from Munich and Dresden. So with this, I summarize the talk with these slides. Thank you very much for your attention.